I'm not gonna lie to you, this is going to be kind of boring and full of repetitions, but if you manage to reach at least halfway through, you will see why in certain schematics the arrows of voltage appear to be drawn upside down. Since the original video ended up being way too long, I decided to split it into two chunks, and while the more interesting part has ended up in the next video, you will need these as a prerequisite to get the full picture later. So without further ado, let's start this video and get it over with. If you happen to be in the 0% of the world population who have endured to watch my two previous videos on voltage, that is, voltage for grown-ups and why voltage is not just potential difference, you already know that by expressing the electric field in terms of the electrodynamic potential phi and A inside the line integral that computes the work per unit charge along a given path in space, you will find that voltage in a stationary system can be decomposed into the sum of a potential difference and an induced voltage term, as shown here. From this formula, it is evident that only in the static case, that is when time derivatives are set to zero, voltage is always, or should I say everywhere, equal to potential difference, while in the non-static case, voltage becomes a quantity that in general, and I have to stress in general, depends on the particular path joining the endpoints. This means that, by definition, voltage can assume multiple values between the same pair of points A and B. In my previous video, I have listed several college-level textbooks that either explicitly or implicitly share this definition. There are many more, but you might still think that this is some far-fetched ivory tower detached from reality lone wolf silly hat-wearing mad scientist theory that is only used behind the closed doors of academia, and that would never be adopted by practicing engineers and technicians in the real world. Well, think again. Allow me to show you that apart from a sign change and a cosmetic difference in notation, the definitions of voltage, potential difference, and induced voltage I have given so far, for the case of stationary circuits, reduce to the exact same formulae given by the International Electrotechnical Commission, IEC, and also by the International Standards Organization, ISO. And what is the IEC, you might ask? The IEC is the Electrical and Electronic Standards Bureau, an analog of what ISO is for mechanical engineering, a sort of super entity that aims to bring order in the chaotic universe of national and regional standards, such as the American ANSI, the European EN, the British BSI, the German DIN, the Indian BIS, making it possible to standardize and certificate products and services across countries all around the world. From their website, we can read that founded in 1906, the International Electrotechnical Commission is a global, not-for-profit membership organization that brings together more than 170 countries and coordinates the work of 20,000 experts globally. The IEC is an organization that prepares and publishes international standards for all electrical, electronic, and related technologies. You know, the IEC of the IEC standards, like the IEC 634 family of standards relative to low voltage electrical installation, the IEC 61557 family of standards for electrical safety in low voltage distribution systems, the IEC 62305 standard for protection against lightning, and the IEC 651 family of standards for direct acting indicating analog electrical instruments, which include, among the others, voltmeters, ammeters, wattmeters, ohm meters, phase meters, and frequency meters. They have to know exactly what voltage is. More to the point, the IEC publishes the set of standards IEC 650 that contains the International Electrotechnical Vocabulary, IEV, which is publicly available at www.electropedia.org. Here is what it says on its webpage. Electropedia is produced by the IEC, the world's leading organization that prepares and publishes international standards for all electrical, electronic, and related technology, collectively known as electrotechnology. Electropedia, also known as the IEV Online, contains all the terms and definitions in the International Electrotechnical Vocabulary, or IEV, which is published also as a set of publications in the IEC 650 series that can be ordered separately from the IEC web stores. Before delving into the IEC definitions of voltage, potential difference, and the likes, we need to clarify that the IEC uses the symbol U for voltage, whereas I use V, and the symbol V for scalar potential, where I use phi instead. Fun fact, the reason for using U for voltage is not to avoid confusion with the unit V for volt, but to avoid confusion with the letter V used to represent the electric potential. We can directly compare, actually equate, the IEC definition of voltage to the definition that was given in my previous videos. The equality is a consequence of the two substantial but also mutual cancelling differences between the respective expressions. The first is the difference in the sign of the integral or integrand. The other is the inversion of the extremal points A and B. The numerical result won't change, but in German-speaking countries you will usually see voltage represented by upside-down arrows, as shown in these schematics. You can find these graphical notation and convention in most books and papers in the German language. You can have a look at Titze, for example, a very famous book in the German language, or at the schematics shown by that guy with a Swiss accent on YouTube. Or simply go to the German Wikipedia page and look up Elektrischspannung. Sorry for the pronunciation. It's even worse than my English. You will find upside-down arrows everywhere on that page. Incidentally, the German Wikipedia page carries a definition of voltage that does not leave much room to ambiguities, unlike the wiki pages from other countries. Notice how it shows its decomposition in the difference in scalar potential and the line integral of the time derivative of the vector potential A. This is the same formula I have used in my previous videos, just the difference that will be explained presently. Perhaps the English, French, Spanish, and Italian pages should adopt this approach in the definition of voltage and rewrite their entries accordingly after adapting them to their notation by inverting the sign of the integrals and reversing the path orientation. But that's just my bloated opinion. The IEC is located in Geneva, Switzerland, a country with whole-riddle cheese cuckoo clocks and 3 official languages, German, French, and Italian. Of the 3, German is the most widely spoken language, and it also happens to be shared by certain European tech giants such as ABB, Bosch, Siemens, Schneider, AEG, Electrolux, and so on. So it shouldn't come as a surprise that the IEC decided to use the German convention and notation in their definitions. Let's now confirm, one definition at a time, that apart from the aforementioned slight change in notation, the integral sign, and orientation of path, the IEC entries are completely equivalent to the description of voltage as sum of potential difference and induced voltage I gave in my previous videos. These is the definition of voltage according to the IEC, and it gives just the integral from A to B of E dot dr. Notice the sign, the order in the lettering. As already anticipated, the removal of the minus sign in front of the integral is accompanied by the inversion in the order of the underscript letters. This means that voltage is defined as the work done by, and not against, the electric field E along a path that goes in the opposite direction as that we are accustomed with. Inverting the orientation of the path and switching the sign of the line integral will give the same numerical result, sign included. This definition and the distinction between the concepts of voltage and potential difference is also adopted by the International Standard Organization, ISO, as we can see from this screenshot. But I will focus on the IEC documentation because it is freely available via the Electropedia website. The IEC notation U sub AB with the integral computed from A to B would be named V sub AB in our shorthand notation and V gamma from B to A in our full notation. Note that the German convention is self-consistent and does not require the inversion of the order of the endpoints, A and B, in any representation of the symbol. It is U sub AB, U along a path gamma from A to B, and integral from A to B. No need for quotes in this notation. Let me rewrite the above formula using the capital letters B and A instead of lowercase a and b. This will give us the voltage as V sub BA, all in capitals, so that it will be easier to compare with the formulae I gave in the previous video. In the rest of this video, I will convert the order of the letters in the IEC definitions from lowercase ab to uppercase BA. With this choice of endpoints, it becomes self-evident that the gist of this whole video is that the IEC notation considers work per unit charge done by the electric field when going from B to A, while our notation considers work per unit charge done against the electric field when going from A to B. The beauty of it is that the numerical values will be the same in both cases, sign included. When voltage is graphically represented by an arrow on a schematic, the arrow represents the directed path along which the line integral that defines it is computed. When the electric field is conservative, voltage does not depend on the path, and any arrow will do. Since in the IEC notation U sub BA is the line integral of plus E dot dl from B to A, while in our notation V sub BA is the line integral of minus E dot dl from A to B, we should expect the arrows to point in opposite directions. And while I'm not aware of any indication of this sort on the IEC website, this is how voltage is graphically represented in the textbooks of many German-speaking countries and also East European countries. So I will call it the IEC notation for brevity. Here is a figure that shows the graphical representation of the arrow of voltage in the two notations. I use capital US here to both mean United States and us, as in our notation. In the US notation, the arrows of voltage point towards higher values of voltage, while in the IEC German notation, the arrows point towards lower values of voltage. To clarify, here is an example with a transistor circuit. We all know that an NPN junction transistor in the active region has approximately a base emitter voltage of plus 0.7 volts, with the base higher than the emitter. For a PNP transistor, VBE is minus 0.7 volts, which also means that VEB is plus 0.7 volts, with the emitter higher than the base. As you can see from the figure, the only difference between conventions is the inversion in the direction of the arrows for all voltages, input and output voltages, voltage drops on resistors, transistor voltages, and so on. In both cases, for an NPN transistor, we obtain a value of plus 0.7 volts, but notice how the arrows that represent this voltage are reversed. In the German IEC notation, positive voltages signify that the field lines of E are predominantly oriented in the same direction as the path gamma, while in our notation, positive voltages are associated with the field lines of E going against the path gamma. I have to acknowledge that there is a method in this madness, since the lettering is consistent with the path orientation. Hence, there is no need for quotes in the German convention. And we do not have to resort to considering the work done against the field by an external force. The German notation has its perks. For example, in this double follower circuit that uses an NPN and PNP transistor to compensate for the BE drop in the first stage. For some reason, I find it easier to follow the dropping and raising of 0.6, 0.7 volts when using the German convention, especially if you use UBE instead of UAB for the PNP transistor. In fact, in this case, the drop and the raise in voltage become self-evident, as you can see from this picture. But that's not enough to make me want to jump ships. If anything, our notation forces us to reflect on the role of the equilibrating external force effects in the definition of voltage. See my first video on voltage for grown-ups, and highlights the need to ideally move the test charge with zero velocity and acceleration to avoid introducing extra energy terms associated with kinetic energy and radiation. But that's academics. Okay, let's see now how to decompose voltage in the IEC notation. It might not be apparent from the above definition of voltage alone, but the IC voltage U sub BA is composed of two parts: an electric potential difference V sub BA equal VB minus VA, which in our notation is called phi sub BA equal phi B minus phi A, and an induced voltage U sub I. It is easier to see this by expanding the integral of the definition one step at a time. Note that I am using the capital letters B and A for ease of comparison. Try not to be confused by the different symbols adopted to denote voltage U and potential difference V in the IC notation. Here is a comparison of the decomposition of voltage with the IC notation and the same decomposition with our notation, where V stands for voltage and phi stands for potential difference. We use the same choice of letters for the endpoints. Notice how the double inversion in the orientation of the path and the sign in front of the integral neatly results in the same ordering of the potential underscripts in the potential difference. Both conventions arrive at the same numerical results for the corresponding quantities, signs included, and it's actually our convention that requires us to put VBA in quotes, because the order that follows the path direction is the opposite of the order of the difference in the integral values. Let's see the IC definitions of the two components of voltage. The IC denotes the electric potential difference by V sub BA equal VB minus VA. In our notation, it is phi BA equal phi B minus phi A. The definition is that VB minus VA equals minus the line integral from A to B of the quantity E plus dA in dt dot dl. In this case, it's named dr. I'm not sure why they chose to show VB minus VA instead of VA minus VB, which would have been consistent with all other formulas shown. Probably the two entries were edited by different authors. Anyway, the formula is correct and represents the potential difference that is part of the voltage U sub BA in the IC notation. I will change the lowercase letters AB to capital BA to make it more easily comparable with our notation. So the scalar potential difference in the IC notation is VB minus VA equal plus the line integral over gamma from B to A of the quantity E plus dA in dt dot dl. In our notation, the same scalar potential difference becomes phi B minus phi A equals minus the integral over gamma from A to B, inverted path, of the same quantity, E plus dA in dt dot dl. As I have already repeated half a dozen times already, the different sign of the integral is nullified by the inversion of the path along which the integral is computed, so we can equate the two quantities. The IC formula is equal to plus the line integral along the reverse path of the irrotational component E irrotational of the electric field. That is the part that admits a scalar potential. And this is the definition of what the IC call simply electric potential without specifier. The electric potential is the scalar potential V of the irrotational vector E plus dA in dt. Remember, this is E minus dA in dt. And it is defined by the formula minus the gradient of V equal to E plus dA in dt. Note how this clarifies that E stands for the total electric field taught, and that V is the scalar electric potential that I have called phi. Also note that in both notation we have that E irrotational is equal to E taught plus dA in dt, and that is equal to minus the gradient of phi, or in the other notation, minus the gradient of V. We have the same expressions for the fields. This is to be expected since the discrepancy in the notations is only about the sign of the integral and the path of integration. The remaining part of the line integral is the induced voltage, which the IC defines in the more general case that includes a motional EMF contribute. I will deal with this in another video to avoid making this one excessively too long. The IEC formula for induced voltage is U induced is equal to the line integral from start point to end point of the quantity minus dA in dt plus V cross B, and all of these dot dr. If we set the velocity V, that is the circuit velocity, equal to 0, we get the following definition for the induced voltage for a stationary circuit, which is U induced is equal to plus the line integral over gamma from B to A of the quantity minus dA in dt dot dl. In our notation, the same value of induced voltage is computed as V induced BA, and we need to put it in quotes because our path is from A to B and not from B to A. Again, let me repeat that for the millionth time, that inversion in the direction of the path is accompanied by the change in the sign of the integral, with the end result that the numerical value will be the same in both notation. And this formula shows the equality. The IEC also gives specific definition for two spatial instances of voltage, namely loop voltage, which we might call EMF, and potential difference, and it also illustrates the very relevant specialization of voltage in circuit theory. All of these In particular, the conditions under which voltage can be considered a simple potential difference, which are general consideration not limited to the IC convention, is going to be in the next video, EMF, PD, and voltage in lumped circuit theory. Did I already mention that I do not know what synthesis is?